Hello. All right. Let's see. We are currently doing some binary operations. Yo. Hey, Com. How's it going? Yo. All right. I've been thinking about this a little bit. So the idea here is basically, let's say you have this expression, and first we take in like these four things. So first like expression, operator, and we're looking at them, and we see that okay, they have equal precedence. So then we decide we group this as an expression, and then we continue doing the same algorithm recursively, but now this is an expression. So this will be the first expression, expression, operator. So now we're looking at these things, and they also have equal, so we make that an expression, and then we're done, basically. Struggle with AOC in Weaver, working on my own language right now. Oh, nice. We're lurking mostly. All right. And then okay, so yeah, so then these will be, yeah, so it's basically that should take care of this here. Now if we have a high precedence, so here's like an example. If we have a high precedence on the right, then we have these four expressions, or these four things: expression, operator, but this is higher than this. Then we group until the end, so we group this entire thing, because we can just shave this off here. And now we're only concerned with this. Now we parse this in expression, so we're concerned with whatever's happening in here. So I mean, we should probably continue to parse this as an arithmetic expression, like recursively. And here we can just see that here we actually see that higher, and now we have lower precedence on the right operator. So that means then what we should do is we should group the left group first, or yeah, group the left before the lower precedence operator, or before the right operator. So basically, these, if they're equal or lower precedence on the right, that means we should group the left part. If it's higher precedence, that means we should group the tail. You could also say it like this is the head, this is the tail. If they equal or lower precedence, we group the head. If it's higher, we group the tail. That's the idea. Right. So, and this was the other algorithm that I was thinking about, but this is way more, I think this is like way more complicated and cumbersome to implement. So I'm just gonna nuke this. I was just checking if this algorithm will work. It feels like it will. It's also a lot simpler because you only have like 2 different scenarios basically, and then it's just a matter of like recursively parsing these expressions. So all right, so what we have now is basically we have kind of like we're building up the components here, which are like value expressions interspersed with operators, binary operators. So that is the components. These components is basically just a list. You have kind of identifiers, literals, expressions, but then you can also have operators. So these 3 are like values, and then this is the operator. So what we do to solve this here is we will look at, well, I guess there's more. If we only have 3 components, we should just return this. This is just one operator. So that's just gonna be a alloc expression. This is gonna be a binary. The operator is gonna be the first item, or this one, index 1. We have left hand side, or what is it called? No. Left, right, span. That is item 0. And I'm gonna make a function called value, maybe. No, wait. This is supposed to be an expression. I'm gonna make 2 expression, maybe. Okay, let's also pass in the parser. We'll switch on self. If we have an expression, we can just return that. If we have an identifier, we can do this. Yeah. If we have a literal, we can also do like 2 expression maybe. And if we have an operator, that means we have some kind of error. So I'm just gonna panic. Shouldn't happen. There's gotta be a couple of these sprinkled around, and to expression integer Oh, I see, it's just a literal. Literal integer what is this? Oh. Oh, it's just a, okay, it's the same. Yeah, that should work. Why am I not getting here? One second. All right. Okay, that's int. Actually, this should be like no. Let's just do this. Float plus element expression literal float. Okay. So now we can just make this. Oh, I see. There we go. Yeah, now we get this. However, I think this should be a try here. Yeah, try. Okay, what are you talking about? You need an allocator or something? No? Key value. Oh, okay. So, but the value is void, so you can just use this to generate like a void value, basically. Where we have typo in enum. Really? Okay, well, if there's a typo in enum, it's gonna get wait, what? typo. Which enum? The name? This one? Or was it this one you were referring to that I fixed? I'm sorry, I'm like jumping around. Member function expression. Yeah, so this would be self. Yeah, okay, good. Operator. Oh, this is spammed. Okay, sure. Let's do payload. And then we are right. It should be 2. 2 expression. Alright. Yeah, because if we only have 3 items, that means we only have this kind of expression, so that should just be returned directly. Span is going to be items 0. Span ends at items 2 span. So let's make a span function here. I thought you have arithmetic letter. Okay. Well, thank you for helping out. Let's see. Span arithmetic about that is I think token span. Identifier just as a span. Operator also as a span. Literal. Alright. You don't have a span function, so let's make a span function here. Actually, this is just inline else. Right. Now it's complaining that we don't return stuff at all points here. Because now if we only have 1, then we want to parse something else. If we have 3, 1, 2, 3 here, then we only have this kind of expression. So that's just a binary expression in itself. Arithmetic state. No? Oh, arithmetic. Ah, you're saying that it should be arithmetic. It should be arithmetic. I thought you meant that it was a capital A. Okay, thank you. There we go. Arithmetic. 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 Yeah, whatever. Parse error. Okay. Yeah, we got there in the end. Thank you. Okay, so now we can basically also we can check like if I was thinking like if we check if the number is odd, it should always be odd. Since if it wasn't odd, we would get an error here. So it should always be odd. So at the end, we will probably do something like a panic shouldn't happen, you know. Why am I not getting this? Oh, I see. Are you doing AC today? No. I did. Well, okay. Yeah, I forgot. There's like AC every day. I'm probably gonna do it. Since I already started it, I might as well finish it. So I do have like now it's gonna be easier because we have this puzzle. Easier to get started, I guess. Because we have the puzzle struct that we can use with arena and everything, so we can read in the file more easily and stuff. Because I don't want to have to retype that every time. Okay, I'm just gonna see if my coffee is ready. I'll be right back. Let's see. Okay. All right. So let's say we now are. So we're taking care of basically these kinds of expressions. Now we need more than 3 though. We need to look and see if, like, we need to look at the 2 operators here, and the algorithm will determine what's happening based on these 2 operators. So we're comparing the precedence of this against this. If this has higher than this, or in other words, if this is lower than this or equal, we will group this as a binary expression, and then continue the algorithm recursively with this expression, or recursively, I guess it's we can just continue, but we're making this as an expression, and then then as we have these 4 items, now we have these 4 items where this whole expression is 1 item in the list. So we're kind of, I guess what we can do is we can remove the first 3 items from the list and then add back 1 expression. And then we do the algorithm again. So we're looking at these 2 operators here, and they are equal. So we do the same thing again. We take the first 3 items, put them in an expression, And then we can see here that we have another one. Well, actually, now we have only 2 or 3 items in the list. We have this expression, the operator, and this expression. So now we're actually done, and we can just return this as a binary expression. Okay, so that's one part of the algorithm. The other part is if it's a higher precedence. So here we have a lower precedence, and here we have a higher precedence. So in that case, we will take the, I guess, third item here and onward, like the whole tail, will be grouped into one expression. So basically we're grouping this as an expression here. And then we will recursively call the algorithm on this inner part. I'm just thinking a little bit about the logistics here, if we want to do it recursively or if we just want to keep on trucking with... Yeah, we probably want to do it recursively, maybe. Because we know that this is an arithmetic expression. We could have a function that only considers, that already has a list to consider. Yeah, that probably makes more sense. Like here, this arithmetic, parse maybe arithmetic expression takes care of everything right now. And it's first we're building up the list of things, right? So we're building up the list of expressions and operators. And then here is where we check the length of components and we decide to what we need to do. We decide what we need to do there, basically. So, you know what? If length is 1, well, if it's an identifier, we need to make a pipeline. Yeah, I think we'll keep maybe this one, and then this, and further down we'll put in a separate function. Parse arithmetic. It's not really an arithmetic. It's more like a binary operation. No, let's make it easier for now. Arithmetic expression, and this would take the parser. And then we also take the components, which is the, well, it doesn't, well, yeah, let's do like, we need the array list of arithmetic components. And we will return an expression. All right. Okay, there we go. So we can reuse this function to check if the component's length is 3. We just return this binary expression. So basically, we could run it here on these 3. Turn it into an expression and also replace these 3 items with that expression. When we're down here, we can now recursively call this function on here and only on this on these. So basically, we could return a binary operation with this as the left-hand side and this as the right-hand side. We would have to do like a bunch of tests to see that this actually works, though. But I'm pretty sure, because we're like, if we're only considering this, like 1 plus something. Well, okay, maybe if we have something that's even lower precedence than the plus. What would that be? Like an AND? we'll do like this, +4 and 5 +1, or something like this. Now this will be a problem, or actually let's do like more than, if that makes more sense. This will be a problem now, I think, because we're only looking at these 4. If we're grouping all of these together, including this, now it's wrong here because, yeah, because of this. Because you would, like, this has lower precedence, so it would, yeah, no, lower. So this would actually, the correct solution is this. And then this, of course. You know. So how would that work? We're gonna have to do like a look ahead. Okay, it wasn't as easy as I first thought. Okay, well, we can still work with the list. So we're chopping this off for now. We're doing that. Now this results in this. I'm actually gonna mark this. I'm gonna do like a marker here. And not a parentheses. Wait. Okay, we could actually do something else entirely. Like if we do this, let's see. So basically here, okay, we have this expression, right? Now the correct solution is gonna be 1 plus 2 times 3 plus 4 is more than, and then 5 plus 1. This is the correct solution. Every binary operation only has, well, okay, this could either be parentheses here and here, or here and here, it doesn't matter. But this is like the correct solution. Now every binary operation only has, you know, left hand side, right hand side, and operator. So there's no ambiguity here. Okay, so if we can reach this point, I believe we have solved the problem. Now what I'm thinking is basically, looking ahead, we already store all different operators in a list, so we already have that in a set. And then we could sort them by precedence, and then we could begin looking for the operators that has the high or no, the lowest precedence. In this case, this one has the lowest precedence, which means we will group like this. We'll take everything to the right and to the left and put them in their own groups. So we'll make a binary expression. Left hand side is going to be the result of calling the function again here. Right hand side is going to be the result of calling the function again here. Now we should also support the case of the components only being one item. At this point we should just return that item to expression here. Yeah, because what could happen is if we only had one item here, then this would be, we call it, we could check if it's one item, or we could just call the function recursively. Okay, so now we have that. Next step. So what if we have multiple though? What if we have multiple? What the? Okay, then we should probably go like from left to right or something. So this would be the proper one there, and then we do this. That would be the solution for that, I believe. So this one more than 3. Well, it doesn't really make sense if it's more than 3 because this is a bool. So it's better if this is like an and or true, except it's gonna be like or like this. But I'll write it like this to make it more clear. So or true or something. So that would be one expression. This is one binary expression. This is the left hand side, and that. And let's. But then this has like lower, even lower precedence. But let's assume they have the same precedence, and then we do a left to right on that. Well, now they have the same precedence. So we can't just take these 3 and do that. We could make a new component list though, where this is one component, another component, one component, one other. Yeah. We could make a new list where we group everything that is not these things. Everything that's between the operators with this precedence will be grouped and then put into a new list. And then we recursively call arithmetic on this inner part. So here's like the next step, or yeah, recursively this would be resolved here. With the pluses like this, and then ultimately it's gonna be this. Okay, yeah, so cool. Okay, so if it's 3, this is trivial. If it's 1, it's a trivial. If it's more, we need to do some precedence checking. First up is to get all the operators. I'm actually gonna move this thing over here. And we'll remove that. So basically, we need to gather all the operators and sort them by precedence. Or well, or we could just do this. We could just have like lowest precedence. Precedence is precedence, yes. It's just it's a U size. We don't need to store them. We just need to find the lowest precedence. So we'll go through all the components. Well, we will we just need to go through every other component, but I was thinking like doing a more you know, efficient algorithm, but whatever. Let's just go through everything, and then we will we check if this is an operator, otherwise we continue. If this is an operator, and then we take lowest precedence, it's going to be the minimum of operator payload precedence and lowest precedence. So then we're finding the lowest precedence. Okay, because then we can use that to find where we need to split the list here. We can actually make like an we can when I say split, maybe we can do a split iterator, a split iterator where each one we will do an arithmetic operation, and then we just go from left to right. Okay, let's see if we can do that. So we'll get the iterator. Split scalar. Wait. I wonder how this will work. So we have components. We're splitting them by operator. However, they are not enums. I wonder how this will work. When it does the comparison, does it just take like equals equals something? Oh, it does index of scalar position. Equal, okay. Because that will work if we put the tag in. The problem though is that I'm not sure, like we're trying to put as you know, the value of t here, but this won't really cut it for that type, because the type actually has like you know, these things in it. So But it would be cool if we could do this. Is there something else we can use? Okay, anyway. Now we can like do while it next. And we get... now we get a list of arithmetic. So this is the sub-components. We get a slice. Yo, two-step. Yeah, splitterator. Yeah, I'm working on the procedure stuff. I think I have an algorithm that works, but it's just a matter of making it now. I'm just thinking here. So we have a subcomponents. We need to parse that as well, like recursively, to get the expression out. But then we know, how do we now create the binary expression? Because we need more context here. We need like the previous one. So if we have a previous one, now we can make a binary expression. Hang on. So now we're here. We have this expression and this expression, so we can make a binary expression here. But then we're left with this part. Like the rest, let's say. And let's say we do make this expression here like this. I'll just remove this for now. Okay, let's say we make this as an expression. Yeah, I mean, maybe we can return a binary. No, we can't do that. Or maybe we can. We take this, return a binary expression of this as the left-hand side. This is the operator, and then we just take the next list of items. But then we have to then we have this part as well. What if we make another list that we put this in? No, we basically already have this list. It's kind of, but we just need to be, the problem that we need to solve right now is how to make a left, starting from the left. How do we make this algorithm so that we can create a binary expression here, then keep this around, create a binary expression here. I guess we could keep it around, yeah. So left hand side is an expression. We also need to keep track of the index. So now at this point the index would be plus equal to subcomponent's length. And also plus 1 because the delimiter is not included here. So once we have previous components, at this point we should have something like, 1 plus 4 more than, and then something else. This is the current item here. This is subcomponents, and this is previous. And then we have some kind of operator here. And now we want to make this into an expression, the left hand side. So we'll do a binary wait. But if we want to look at path parsing and found something zig based on a math-clad article. Oh. Yeah, it's gonna be a little bit easier to read for me. Okay, I'll check it out. I'll just try to finish this thought here. This would be prev subcomponents. Actually, you know what? This would now be the recursive call here. So this would be parse arithmetic expression on previous subcomponents. Good morning from Boston. Right, very early. How early is it? Parse arithmetic, yeah. Alright, and then we have the right hand side. That's gonna also be parse arithmetic subcomponents. Right, so now we have left and right. And we have the binary expression. I'm gonna call this the binary. It's gonna be this is gonna be left, right. Oh, that's early. Yeah, no problem. 2-step. Thank you. Let's see. And the operator now is gonna be like index plus subcomponents length. I think that's gonna end up being, because let's say we have one item in the subcomponent. I is 0. Yeah, that's gonna be correct. The right one, and then the span. Actually, now we could just take left span and right span. Okay. Okay, so now we have the first part here. We have now this is in the one expression. So now if we have a binary already, that's going to be the new left hand side. So let's make this into a null. And here is like if we have a binary, that's going to be the left hand side. And then we do this, except we don't do the left hand side. Else we do that. I mean, here we could just do next directly here, because we know that we should have at least 2 of these. Are you one of the rare people who use Zig professionally? No, only as a hobby. But it would be cool to start building, you know, developer tools in Zig. But it's more like a fun exploring part for me with programming right now. Yeah, so we should have at least like 2 of these. So let's grab 1. And then we should be going. Okay, let's do. I'm just seeing how I can simplify this a little bit. Let's do that. Let's have a continuation expression that says prev to sub. But we only need it once, though. Actually. You know what? Let's change this to left-hand side. We're changing that to left-hand side. We will start it by being parse arithmetic. No, wait, that's... Yeah, no. We'll start it by grabbing the first one. But then we don't even need that. So that's our first left-hand side. And then we should always have it, so we don't need to do this. Then we just need to pick the right-hand side, reassign the left-hand side with left being left-hand side, the previous left-hand side. So that's a walk from left to right. And now we can skip this here. Okay, yeah, that's much more simple. What language do you use professionally, or do you work as dev? Yeah, I'm using mostly TypeScript in front end right now, but I have been also using C# on the back end, and also PHP some time ago. But right now it's mostly TypeScript. Either Sig tools, org on GitHub, I have ZLS and lots of related stuff going on. Oh, I see, I see. Is that the thing that you posted? Or... No. Wait. Oh, sorry, if it responded to something else, I don't know. Okay, this is left hand side, yes. Right should be. Why is this not working properly? Oh, you work with Go 10 years there? On like some kind of web backend or something? Okay, here we will just return parse arithmetic. No. Arithmetic, sorry. And we just pass in the components. We will deinitialize them, yes, good. Yeah, there we go. This would be self. I see, let's do this. Actually, we don't need to modify it, so I'm just gonna copy it. Actually, in that case, we don't actually need, we just do this. There we go. I suppose might be interested in making the tools. Oh, I see, I see. Yeah, okay, okay. Yeah. Cool. Thank you. I was thinking like, you know, specific to the work I'm currently doing, like on like in my job, basically. I usually create little scripts here and there to do stuff. And that's also why I want to make this language, to make it easier to do that. And but yeah, Zig is interesting as well. Like, but that would be more like, okay, I don't know. It will probably take longer to do things in Zig than to just, if you just want to make some quick script. I've done a lot infrastructure, event resistant, Kafka, mostly API dev, don't do much web stuff, unfortunately. Okay. So what for? Okay, sorry if I'm being nosy, but what for if it's not for like some kind of web system, like you know, like Kafka? Can you use that for? I mean, I guess you could use it for whatever, but I should also finish my language to force my coworker to use it. Yes. I also like the fact that I'm building it in Zig. It feels like some kind of power move. No. It's fun. Variable of type, comp time in must be constant comp time. Yeah, you are a usize, so there we go. There we go. Now we get this issue here. So that's unfortunate because I would really want to be able to do this. I mean, we could just go in here, copy this code here, basically. Where the delimiter is like it's not exactly the same type. It's like it's like an enum. Yeah, see, everything works with the same type. Unless you can change the types somewhat. I guess we could like just say undefined. That will, you know, if you have no. I'm just gonna try this. Expect equal 1, 2. Yeah. So we can run this. So basically, if you what was I trying to do here? Yeah, let's say you have an enum type or union enum, and we have like int or int is a usize, float, f32, bool. Okay. Now all of them have values. So when you create a type of this thing, let's see, this is like UE int 5, right? But in Zig, you can do things like UE equals int to check which tag it is. And this is what I want to use here. So, but if you have a tag that you have to supply as this type here, let's do like UE tag is UE dot int equals, let's say it's undefined. Now let's see if we can do this. So let's do like try testing expect UE to be equal to UET. Now hopefully this would just check the tags. It's not allowed. Okay. But what if this is the, no, that doesn't work. See, I can't make this into the tag type because it has to be type UE. So it's like you can't do this because that requires things there. I can't do, you can't do this. This is just a tag. There's even like, if you do like enums, no, meta maybe. You could do like field enum of UE I mean, this works if you take the tag type if you do the tag of UE, you can do this. This should work, yeah. But the problem is we can't pass the tag as this type. If this is a UE, we can't set this to be this. So there's our issue. But I want a scalar or a split iterator that could take, you know, the type that you're iterating over is a union enum, and then you want to match against a tag instead. So let's go back and let's go over here and let's go over here, and I will copy this and I will go to, I don't know, source mem split, and we'll make our own split thing. Yeah, two-step. The problem is that here there's two problems basically also. Like here, this expects a value of type delimiter, so you cannot pass a tag in here because that will try to make it into that type, and that doesn't work. It will try to make it into the arithmetic component type, and it doesn't work because it expects a payload in the with the tag. Basically, that the union enum with only the tag, and then the value is like a void, and that doesn't work. It needs to have a value. And then the other problem is that when you try to do equals equals of a union enum to another union enum, that is an invalid operation, so that also fails. But if this was a tag instead, if this was the tag of t, then it would work. So we have to change the type here to a tag of t. Yes, it does get the active tag, but we can't use it. That's the problem is we can't pass the active tag in here. But we have to do. Yeah, it does work, and it even works to do active tag x equals y. You don't have to do them both. You can just do one, but that's not the problem here. The problem is that this type is arithmetic component, which is a union enum here. So this list is a bunch of arithmetic components. Then it wants a delimiter, which is also an arithmetic component. But we cannot pass a tag here because that will be an error. Yes. But we can't do that here because this expects a union enum and not the tag of the union enum. As I shown, well, I removed the file now, but I showed that it basically it's a compiler error. But basically what we need is we need a split iterator with two types. I mean, actually we don't need two types. We need one type, which is supposed to be a union enum. So this is split iterator of union enums. So we expect T to be a union enum, and then the delimiter doesn't matter. Well, the delimiter is actually gonna be a I guess you could keep this kind of thing here, So this is going to be the tag of t. So why not pass in union with tag equals undefined? That doesn't work. Also because well, it works. That's what I tried to do here. It works here, but it does not work when it tries to do you know, item 0 equals equals undefined, because this results in an error as well, because there's no, you cannot do equals equals on two union enums. You have to use a tag. So this has to be like this, and you can't pass that in. Yes, but the whole issue here is that this is the built-in function, so I have to copy it and make my own version that does that. Like, I'm not doing the equals equals, it's this function that produces the type that does it later. Like when I do next here, this is now the standard library, so I have to make my own version that can support basically this the tag type for, I mean, I could even do like delimiter is gonna be the tag of t. And this could also be that. Yeah. Now these are also using like index of, and that also needs its own version then, like all of these. Man. Haystack needle is the tag. Oh my god. Let's just forget about the sequence. I'm just gonna do the scalar. Right. Yeah. Yeah, the split iterator is great. But in this case, it doesn't work. I mean, I could have also changed something else about my algorithm, like changing the type of the array or something. I don't know. But I feel like this should be something that could be cool to have, but I don't know. Start index. No, forget about that. Wait, do we need a start index actually? Yes, we do. Okay. Yeah, because it's position. Let's just get rid of this. And we'll get rid of these. There we go. Start index. All right, let's do. If this is more than haystack length minus 1. Wait. If this is more than or equal to this, because minus 1 we should also be able to do it. So then we return null, because otherwise this, if the left part here is larger than the right part, this will be an infinite loop. I don't think they because this is like runtime now, so we don't know if the left part, but there's no guard against it either. So you will actually get an infinite loop here, I'm pretty sure. Like I've been there before. So you have to guard against that case before. Yeah, sorting, yeah. No, not meta. Sort. Yeah, you can provide a less than function. Yeah, exactly. So it would be cool if you could have like a more generic splitterator. All right. It also brings me back to the generic iterator thing I did in the game code. Okay, so let's see. So if this is more, then we return null. Otherwise, we try to look for it. Then we're done. No, we return not h. Yes, we return I. And here we do haystack. I, and here we do I. There we go. Okay. Delimiter type. Alright, fine. Okay. I'm not gonna add any tests. I'm just gonna assume that this works perfectly. We could add tests, you know, test. Just to make sure. So let's have a list. So let's make like an enum, union enum. Yo, oh my god, what's up? Just making a scripting language in Zig. What are you doing? So let's have like, I don't know, 1 is use size, 2 is a float, 3 or sorry, f32, 3 is a bool. Then we will create a list which is a bunch of UEs. So we have like 1, 2, and 3, and then we have another 1 or 2 and another 1. Okay, that's our list. Now we'll create an iterator on UEs. delimiter is, yeah, so delimiter is gonna be a tag of UE, which is gonna be oh hey, it works. It's gonna be like 3. Wait, actually it doesn't work. Okay, it's gonna be 3 there. So we should get 2 items. We should get this list and this list. Okay, so the delimiter is delimiter. The buffer is list. And index should be set automatically, I think. No, let's just set it to 0. Okay. And then we will do first is next, and second. Now we can do expect equal slices, maybe. One, 2, and then the actual is first. I'm not sure how it does it if it does like a deep comparison or something. And then this one will be 2, 4.4, and 1, 5. Oops, on this. Sequence. Oh. See? There we go. It works. Awesome. Okay. It's so nice when it's very easy to make the tests. I recently discovered this, that you could just do like zig test on this file. However, it runs it in kind of like its own context. So basically, if it doesn't depend on anything else except for like the standard library or things in the same directory, there would be maybe some issues. But for, you know, files like this where you don't have any dependencies and stuff, it's super easy to create a test and then just run it like this. You got an example of how the language looks like? Yeah. It's very early right now, so we don't have like many features or anything. But this is a functioning example here where I'm showing off like closures. So basically you can create, now this is a mutable variable, you can also have constant as well. And then here's a function, and then we show that we can modify A with this closure here. Now keep in mind that this could be changed in the future, that this A will be, because it's this primitive type here, it might become a copy in here instead of a reference. Right now it's a reference to this, but it could become a copy as well. So there's no semantics of referencing variables or anything like that. This is all like very early stages right now. And also to note that this is gonna be like, this is just like a toy language that I'm sharing it, but it's basically just gonna be me using it basically to replace bash with, hopefully. And it's mostly like a fun learning experience for me making language. Yeah, so basically here, so we have like, you can call echo here with and then with the arguments we have a string interpolation, and then you could call the functions as well. And also you can import library. So this here we have like lib rn. So you can do lib equals import. Well, why doesn't this work? Okay, the auto completion stopped working here for some reason, but we had that working at some point. Maybe no. For some reason it stopped working. But anyway, you can import libs and call functions on those as well. So you can call like lib hello here. But it's very, very early and there's not many features right now. You can't even do like this. This is what I'm working on right now, so that you can actually do arithmetic operations. Zig is a little simpler when you use file imports instead of modules and put tests in the same file. That way you don't run into a file that exists in multiple modules. Right. Yeah. I like Zig's module system. It does make sense. And I'm trying to kind of mimic it in my program language here, but there's some differences in the languages that makes it a little bit different. But yeah. Okay, so where were we? Parser. Oh yeah, the splits thing. I want to make a function now that exposes this now. So split iterator. So split scalar union enum. Constantly type, and we get the list or whatever it's called, and then we get the needle, or I guess haystack needle maybe, and now this is gonna be the tag of t. There we go. And we'll return a split iterator of union enums with t scalar. There we go. And then buffer is haystack. Delimiter is needle. And that's it. Cool. So now we'll go back. Actually, let's go to root here, and we will expose this as well. Split scalar union enum. Now we can do mem and now we can actually pass in OP here. There we go. Okay. If you look at how as standard is written, as uses import standard.zig everywhere. That's why what I try to do whenever possible. I think std does it everywhere. What? But this doesn't work, right? Or is it like a new thing? Ah, from within. Okay. But how does it... But it doesn't work for like subfolders, right? Yeah. This is what annoys me. I don't like... I mean, I like relative imports when it makes sense, but I also wish there was a way to import from the project root as well. So you don't have to... Or make aliases, so you don't have to change the import paths if you move files, for example. Expected found. Okay. I think... Do we have the whole thing now? Or did we miss something? Yeah, we have to return here in the end. So in the end, we would run out of these. What happens then? We should have a left-hand side with the left-hand side and then subcomponents. So we just return the left-hand side, yeah. All right. Now I can't run tests in here because we're importing outside module path, but I believe I have zig build test. Okay, we still have some issues here apparently. Binary op has no... Oh yeah, we need to make that, right. AST binary operator. Let's make from token. Yeah, we're basically just doing this. Let's take all of these and try to so this would be like plus minus star slash remainder is percent, greater is percent, greater is, do we have greater here? It's just greater. Greater equal, we all also have less This is bang equal. Equal is a sign. It's kind of weird how that works. And then logical and is keyword and keyword or. There we go. I'm actually not sure about that. I might keep it, you know, ampersand ampersand. Maybe you can mix it up. Maybe you can use both ampersand ampersand and pipe pipe. The problem is though, in bash it means something else, and I do want to keep that, like piping something and then, you know, and will, or whatever, forget the pipe, but if you have a executable and something else, it just means evaluate the second one if the first one succeeded. But this is more like a Boolean operation here with the keyword and keyword or. So yeah, there's a bit of nuance there because it could be used in a Boolean expression. It could also be used in like a pipeline stage thing. So it's gonna be, yeah, we'll figure it out. Let's do it like this for now, and we'll figure it out. So all right. That's everything there. Handle all possibilities. No, if it's something else, we will just panic. Maybe. It's gonna come around to bite me in the ass. At some point. At least it's easy to find those. Alright. Out of memory. Oh, wait. There we go. Oh, this wasn't actually used. The initialize. Let's see. S. Okay. No more compilers. We now have parse maybe arithmetic expression. This is now wired up when we have an identifier. It does not currently work if you just have a number. So it only works for identifiers right now. But we could just plug this in if we're dealing with a number as well. Also, once you're in like the arithmetic expression machinery, we don't have support for like other variables. Well, actually we do. We have identifiers. I'm just joking. Okay. So we have that. But we need to put this in where, if we're parsing like a primary, I think maybe. And here we can have literals and stuff. True, false, null. parentheses. That just solves itself. If we have anything of this sort, we also want to check if we have our arithmetic expression. Maybe we'll do that beforehand. So if the next one is if we, let's say we're here, and then we'll do next one again. We're peaking 2 now, and let's just grab out the second one. If, or we switch, no, we say if peaked you know what? Let's return null here. If we got an operator that we don't care about, we will return an arithmetic expression. Let's do maybe arithmetic expression. It's either going to be an arithmetic expression or it's going to fail. So I will do this. I guess we don't need to try if we're returning an error. Then I guess also this will fail if we don't have more than 2, perhaps. No, we'll get like end of file actually. Yeah, we're just gonna get a bunch of end of files, so that doesn't matter. Yo Penguin, what is that? I can't really see. That I have to go and look in like the Twitch thing. Oh, it's hello. I'm just watching the chat from OBS, so I can't, like, some of the things does not show up there. Okay. Right. So if it's a binary operation, we will parse an arithmetic expression, which is kind of weird because it could be like a boolean, but we don't have support for that right now. This is how it's going to be now right now. Otherwise, we'll return this. Let me do like break. Actually, we don't really need that. We can just return directly, I think. Expected optional type. Oh, I see. We need to do this. Okay. There should be an error somewhere, yeah. Here. If this doesn't work, we're gonna do... Should we just return null here as well? And we'll put these here instead. No. Oh, I thought I fixed this. God damn it, you have to spell it out. Okay, whatever. Yeah, it's just because where you have like a or else here. Otherwise, it works. I thought I fixed it because it worked with, I think try works and maybe catch. I'm not sure. But all right, fine. Maybe it has something to do with like the resource location or whatever it was called, like inferring the types. All right. Like, does this work? Like, if you do as this, does that work? No, because now it's a null. Now it's an optional. What if we do this? That doesn't work either. That works. Okay. Token spanned. There. All right. No more errors. All right. So now technically, I think we should have stuff. Let me get rid of all this. Right, let's do var so we can try runic parse ast or print ast. Test it. All right. Okay. What about 5 plus 2? It works, but we don't have printing of the thing. Do we have execution of this? No. Okay, so we need to do. I just want the printing to work because, yeah, it's nice to see how it looks like, especially now that we wanna see what kind of expression we get. So let's do print. Sorry, printing not implemented. One of them is statements, one is expressions. Here's expressions, I think. Maybe, no, yes, no. Yeah, it's expression, okay. So we'll do binary. Right indent. Binary. This is just print all actually. Print span in line. Oops. All right. And I guess we'll do like left, right, rider, right all left, and then render expression. Expression is going to be binary left. Level is level +1. Okay, and then we'll do right. And there we go. Oh yeah, and then we need the operator. We need the operator as well, yeah. So operator. Let's have the actually let's do operator first. Which should just be print. I'm just gonna take tag name of binary operator. Okay. Operator. There we go. No, there we don't go. Okay, there we go. So we have operator add, left is a literal integer 5, right is a literal integer 2. There we go. Are using formatter. A zig. Zig has kind of like a built-in formatting. So every time I save, it's formatting for me. Or are you talking about this this thing we're doing here with the code? Like we're printing out the stuff. It's basically just you have a level which is the indentation level, and right indent is you have to manually call like right indent, and then we just write. So it's we're basically creating the format here. If you're talking about that. So basically, so here we add a level. Here we call like parse, like render expression AST with the level +1, or yeah, so that in this context level is already here, and then this will be +1 relative to this. Yeah, the built-in one. Yeah, so if I add a comma here and save, it's gonna format it like this. So there's like a built-in formatter, which is super nice, because then for one, you don't have to set up your own formatter, or yeah, you don't have to spend any time. Like I don't remember last time I tried to manually. I used to do that all the time before, like manually format everything that I wrote. I'll tell you, the worst formatting that I've seen, there might be others, but the worst one I've seen, it was like the older Visual Studio in like C#. That was a nightmare, because it would like do some kind of thing like this or something. I don't know what was going on. It would do something like this. I have no idea. But yeah. But this one is really nice. It works really well, I think. There's some things that it can't do that kind of annoys me, but it just makes me kind of restructure my code instead to make it look nicer. Alright, so now we can do that. Now let's try a more advanced one. So let's do like times 3 + 1. So this should be, you know, this should be now grouped together. So what we should see is we should see, also we should try parentheses, but we should see this expression and then this. So this would be the thing we should see, I think. So first we start with this binary here, where we have plus, left hand side is this, right hand side is that. And then in here we would see left hand side is 5, right hand side is this expression, and this one is like this. So I think this is what we should see. Let me do this. Oh, and I have to remove the parentheses. Okay. You can see here we start with an add. That's correct. Left one is also a binary. Okay. The right one is literal one. Hey, that works. Binary left. I mean multiply left is. Wait. No, this is not correct. Or is it? No, this is not correct, I don't think. It should be add 5 to multiply. Yeah, this is wrong. We're adding 5 and 2 and then multiplying by 3. That doesn't work. Okay, what is going on there? Let me think about this again. The way the algorithm works is basically we're looking for the lowest precedence first. So this should be the... No, wait. Yes, we're looking for the lowest precedence. So this should be the lowest precedence. And then we get this as an item in the list, in the splitterator. This should be an item and this should be an item. So we take the first 3 items. No. What the hell did we do? Yeah, we take this as the left hand side and this as the right hand side and make this into a binary. And now this is the new left hand side. Then we take this as a left hand side and this is right hand side. But there's something wrong going on here. It makes this into the left hand side instead. Multiply has higher precedence than add. We're finding the lowest. Yeah, we can't use min, like standard min, because of this is not like a number that you can do. We have precedence, although it could be cool if we could kind of make a type class, but we don't have that. So also you can't implement like the operators in Zig. So that doesn't work. No, it's not math min, it's mem min. Yeah, you cannot do the min operator. Yeah, that doesn't work. But yeah, so we have to manually find the lowest precedence by taking the min of the precedence and then the current lowest precedence. Is there no min by key? Like there would be cool if there was, if you could do min by function or something, and then you provide a function that will extract the min value, so you have to call this function every time. Although that is not like very optimized. So if you look at this is using min, which works with numbers, but it also works with like vectors as well. Although this does just a loop here. so we don't really use, but you can use min from like a, if you have two vectors, but it doesn't really make sense here because we're trying to find the minimum in the entire thing. So, but yeah, anyway, we have to have it like that, and then we split the thing up. I probably want to log out, since we don't know if this works for all edge cases or whatever. We just have one test for this one, so for the split scalar unit enum. So let's create this here, and I will try to show whatever components are in here. Let's do an F, like formatting, and this would be subcomponents. So this would try to call a format function on these things, I'm pretty sure. And so let's go in here and we will create a format function, which we don't really have. It's just a, we just take self arithmetic component, and then the writer is standard IO writer, except it's a pointer, and then we, whoops, and then we do this. Someone is blasting outside. Okay, anyway, let's see. So this would be like switch on self. If we have an operator, we just do they're playing kind of music that makes me think that some kind of alarm is going off here. Okay, this one is, no, we get the operator here, and the payload is, then we just take the tag name. All right. If it's an expression, we would write print parentheses, and then in here we would do format oh no, this would be like, yeah, I'm just gonna do expression there because we don't have a way to print the form. Well, we do have a way to print expression, but not like this. So I would just write that. Why did that turn white? Oh, writer. Identifier. Let's just do this, I guess. And that's gonna be print. And then we have what, literal. We could actually take the span, take slice from self. No, we would need a parser for that. Okay. I was thinking just take the like the lexeme. Actually, we should. Actually, we could just take the lexeme here. No, we can't. We don't have the token. Ah. Okay, let's just do switch on that real quick. We do inline else writer print and then this is one of these. Okay. Int and float. Print. Actually, this will be just write all. L.text. And then we have bool. Which would be like bool.value. There we go. I don't care about you. Okay, now we have the format function there. So when we do the thing here, we now, this should, because this is a list of those, so it should go ahead and call format on each one of the subcomponents. Perhaps. I don't know. I don't actually know. I haven't tried this. But let's see. It didn't crash at least. Well, maybe it's not building here. Yeah. Okay. No field name find format in the slice. Great. How do you do that then? Can you have a format? Where is that documentation? I can never find this, like the formatting documentation. Here we go. Formatter, argument specify field argument with precision. Arguments in numeric index and field name. Arguments should be inserted. Using a field name, you are required to enclose the field name. Oh, I didn't know that you could do this. What the hell? You're required to enclose the field name in a square brackets score, as opposed to numeric index, which can be written like this. Specifier. Okay, wait. So can you do this? Or do you have to do, wait, is it this? What the hell? Argument specifier. Argument. Okay, maybe you can't do that. I was thinking like this is like a range. Specifier type dependent formatting option dependent type should be formatted. Yes. Width, total width, the bytes, okay. Only exceptions to fill parameter. So it doesn't say like if you provide a slice, it will do something. Print value. Format. Format length. If it's 2. Okay. B64. So what I'm looking for is basically a way to format an array. I thought it like automatically did it, but you can also wrap the type in. You can wrap the array in another type that will have the format function that you want, but I just want to see if there is a way to do it here. So we're switching on type info otherwise. What if it's an array? Where are you? Pointer, slice, is any. What? I don't get it. Okay, let's just do this. We're gonna wrap it, so this is gonna be const arithmetic component, and we're gonna have a format function. There has to be a way to do it. And we just loop through. And then we do try writer print format item. And now we wrap this here. Okay, no field name boolean. There we go. That solved it. Okay, let's do build. We go to test. Oops. There we go. Okay. Wait. What the hell? 2, 3, 1. Oh yeah, it skips the first one because we already got that. So the first one is gonna be left-hand side. No, but that's now an expression. So I'll take the first component. It's gonna be this. Okay, 5, 2, 3, 1. That does not make sense. It should have split. It should be these two with the operator and these two with this plus. And then the multiplication like is not is like no wait. It should be the first one should be this, and then the second list should be this 2 and 3 with the multiplication. Yeah. So why are we not seeing that? It's like it's splitting everything. Test does succeed here. We have the basic case here where 3 has a where 3 is the delimiter. So basically skipping this and you get this one as a list and then this one as a list. So it should be the same here. We are first getting the 5, which does make sense. But then we should get 2 and 3 in a list, not like 2 and then 3 and then 1 in separate lists. So why is that happening? It has to be something wrong with this, with the union enum here. Split scalar union enum. Hang on. What the hell am I doing here? This is wrong. Oh, shit. Oh, man. We need a more advanced one, actually. We need... Okay, this is nice, but we do need... we need like a function. This works on all the operators. That's why this is how it is. Okay. We need to be able to pass a function instead. We need another one. I will do let's split iterator with function or by function or something. And then I mean, we could put the function here. We could have it here. It doesn't matter. Delimiter is gonna be... I mean, okay. Yeah, the type is going to be a function that takes a t, produces a bool, which determines if it's supposed to be a delimiter or not. And if you want to have like sequence, oops, you could have, yeah, that would still be the same thing. I think you would, no, wait, this would be a little bit more tricky though. Yeah, I don't know if you can have that easily. There's probably some way of talking about that, but and this would return a bool. Now we don't really need this tag anymore. Where is this happening? Over here. So here, instead of doing index, well, we need to change this as well by function. There we go. And instead of the needle's actually going to be a function now. So it's going to be a function that takes a t and returns a bool. And if the needle works on the haystack, we return the index. Alright, now you need to be a function that takes a t and returns a bool. So now this would be limiter function. We need to create a function that has a closure. So then we need to create a struct. Because the function will look like this. We have a function called isDelimiter that takes an arithmetic component and returns a bool. However, we don't have information about which is the delimiter. We would need to basically say that the component needs to be an operator. If it's anything else, it's false. And the operator precedence needs to be equal to the lowest precedence. However, we don't have this, so we need to store this in our struct, and then here we actually need to have this context. And that means that we need to change the function signature. I'm just gonna say delimiter function compline t is gonna return a type, and we'll return a function that takes self. So we need a context type as well. Self is context, and it takes that and returns bool. Okay, this will be a delimiter function of t. Well, okay, now we need a context as well. However, the context we can just pass in. So context can be an any type, and we can just pass in type of context there instead. so we don't have to like pass in the context type every time. No, yes, yeah, because we need the context as well. So the delimiter is the needle. We need the context. It's gonna be context. You will need the context as well. And here we should also store the contexts. And then you are a delimiter function, context t. And now you need a context function as well. So this would be, yeah, also type of context t. We pass context there, and then when we call this method, we have to pass context as well. And then here we have to pass context. There we go. And here we have to pass context. Okay. Now down here we have to change this a little bit. We need a delimiter function. Context is gonna be Boolean, so it's gonna be like the value of this like thing, and then the function is gonna be is delimiter. Where we have self and we have the UE, and then we return a bool, and now we can just return self context is equal to UE. Well, switch on the value. It has to be a 3, and if and then we get 3 out. If 3 is then equal to the context, no, the wait, that's not the context. I'm gonna call this the matcher, I guess. If that is equal, then we return, well, let's just return this. Otherwise, return false, or don't have to say return twice there. We have return here. All right. What? It's not unused. Well, okay. And then the delimiter is going to be a delimiter function df and then ue, which is equal to df.isDelimiter. I guess I keep the signature here so that the types will work as well. And here's the list as usual, and then we split by this with the delimiter, so that should all be the same. And then this should be the same as well. So we only change like the delimiter part. So now but the thing is now that this should match on. No, wait. Yeah. We need to pass in the context as well. So we need to actually create. So this is the delimiter function, and then we have delimiter context, which is a df, and then we say that the matcher should be false. Let's say so. This should match on this type, on this value, because the value is false. And then we can, well, let's just remove that, because we can just say delimiter now here dot is delimiter. Okay, and then the context is going to be delimiter. Actually, let's call the function instead. Context delimiter haystack is list, needle is delimiter dot is delimiter, and that's it. Okay. Is there anything else we need to do? No, field name is delimiter on struct. It isn't. I don't understand what's going on here. Whoops. Why can't I do this? Use of undeclared identifier df. Is it because it's in a test or something? Okay, let's move these out. I guess it's nice to do that anyway, because yeah, because we can reuse it for other tests. Okay, no field name is delimiter in struct split df. What? Okay, what if we do this? Whoops. Okay, there it works. I'm pretty sure you should be able to do that. Maybe you can't, I don't know. Because this is a member function, because it's self, it's df, it's itself. Yeah, okay, well, whatever. It works. Now if we make another test, let's say test 2, very descriptive here, and then we change this to true. Now we should just get one, we should get the whole list now. Yeah. All right. Cool. Okay. Now we have a way more generic split iterator. So this should still be correct here. Self, I'll call this context, switch on, that will be load proceedings there, What the hell? I've never seen that issue before. So what is the type? It's the limiter function. Okay. Okay, anyway. Now we need to create the limiter for this. So this will be the limiter function, and the lowest precedence is lowest precedence. Right, so now we basically kind of have like a function with a closure. The downside is you basically have to manually pass in the closure. So that's kind of like how it works. But we're kind of making it ourselves here. Now we can use it here. The limiter, well, we're gonna have to do this, I guess. Is the limiter. And then we have to pass in the context as well. So this would be the limiter. There we go. When you have some time, can you share us how Zig achieves polymorphism as abstraction interfaces? Many generic structures are things of dispatched and interfaces. I mean, I can show you a little bit in soon. I just want to test this here, and I will show you a little bit of that. Okay. Now this looks better. First is this. Now we get this, and then 1. Okay. I should have had some kind of expression like writer that writes the expressions as code instead of this here, so that you can more easily see these things. But this one is basically operator add, left, multiply. What? No, this is wrong again. Multiply again? Wait, did I change the code? No. Multiply 5 by... Okay, this doesn't make sense. Why is this multiply now? Could be something wrong with this here. Actually, it is something wrong with that. I should start at first components length, because we already skipped past the first one. And we also skip past the first delimiter, so we start here, and then this would actually be now I -1. Add, boom, it works. Yes. Okay. Okay, I'll just go ahead and do the execution real quick, because I think the execution is way easier than the parsing of this. So I will go to evaluator, evaluate expression, binary. Switch on binary operator. Add it's not as easy as it seems. Because we have different types. We have floats and ints. What happens if a int should coerce into floats? Okay, left is self-evaluate expression scopes left. So there we go. Now we have left. We should also get right. Right. Now left is a value. We have a bunch of stuff that it could be. It could be a bool, it could be a float, integer. So yeah, so this is where we have to do some kind of a little bit of semantics in the execution here. I can show you now a little bit, since this was not as easy as I first thought, as per usual. Okay, we can do some I don't know what to call it, generics. All right. So in Zig, there's like a lot of different ways you can do generics, and the support for generics are basically you have a thing called union enums. You can use that. You can also use comp time to kind of create interfaces as well. The downside, so there's like pros and cons with each approach. I can think of 3 major ways to do it. So the first one I'm going to show is like union enum. So let's say you have a, I don't know, let's just say an expression here, union enum. Now the good thing about this is that you would get different kinds of values here. You can have like, let's say you have a number, which is a float. Let's say a float. Let's say you have a string, which is the string type here. Yeah, let's just start with this. Okay, so this is the, because now you can have a function that is like, I don't know, add 2 expressions. So expression 1, let's do like left. I'm basically trying to do the thing I tried to do at the other thing. But let's say we take 2 expressions, right? Now we can talk about these types as expressions, which is very good. And then we return, I don't know, an expression probably. So yeah, it's gonna get a bit convoluted here, but basically what you do is you will say, you can say, for example, you can say if left is a number. So you can do this check here, and if right is a number, then we can return a new number that is left number plus right number. Okay, this is one way of doing it. And then let's say that we do like number is a string. So if both of them are strings, then you can't really concatenate strings in Zig using this, but I'm just showing here how you would do it. Like how you would actually need to do this is you would need to have an allocator that kind of puts the strings together. But I'm just doing it for demonstration purpose. Actually, let's change this from a string to what do we have that could be added? I mean, okay, let's do like ints and floats instead. So this is an int and this is a float. Let's do number to int and string to float. Right. So this works. Ints can be added to ints, floats can be added to floats. So it's kind of like what's actually happening is that this has an explicit enum, which we can explicitly, or implicit enum, but we can explicitly also define it if we want, which is an int or a float. And then you could put the expression enum in here. So now, you know, these correspond to these here, but the union enum actually attaches like types here. And that's why we can equate with an int. So it's kind of like doing introspection on which type it is on the enum. Okay, so that is one way of doing it. You know, you're talking about an expression which could be several different types here. That's one way of doing it. Now let's see. Another way is the way that they do it in. Well, let's just do one very basic way, which is kind of stupid, but it's also it is a way to do it. So let's say you have different types. Let's say you have like a number type. This is just very convoluted here, but let's say you have a number type, which is i32. Let's say you have float type that is an f32, right? So they both now have, if you notice, they both have a field called value, and we can exploit that. So we can actually say, let's have a function add. I'm just going to call it add underscore. So this would take left hand side. Now what do we put here? Because we have two different types. Now you can't just do this, even though it would be kind of cool. You can't do this in the Zig. So what you have to do is you have to do any type. Well, this is one way to do it. You can say any type and write any type. Now any type is, it does expect any type. So you can't put anything in there, anything at all. And then you would get the result, which we actually need to like calculate here from these types. So the result will have to be calculated from the types. And what you could do is either you can have like a break block in here to calculate that. We can also have a function that is like add, you know, and then we have like type of left, type of right, and that would calculate the type that we return, because the return cannot be any type. We have to actually calculate the type. So let's say we have this add function and we have like left is a type, right is a type, and then we return a type, and then we're gonna do the same thing. So we're gonna say if left is equal to number and right is equal to number, we return a number. Or, okay, number was maybe the wrong thing here. Let's call it int. Or if they are float, if both are float, we return a float. Otherwise, I'm gonna say we have a compiler error. So cannot add, and then you can do type name int. Now this plus plus can append strings, but it only works in comp time context. Cannot add a thing with a thing. And then this is, no, this is right. And this is left. Alright? So if you don't pass in the correct types, this will be a compiler error now. So we're kind of defining our own rules here. And otherwise, what we need to do is we need to just say left.value plus right.value. Except we need to also wrap it, because the type is actually gonna be, no, okay, let's actually do like I32 here and F32, so we don't have to wrap it. Okay, so now we can just return this. Now if we do a test here, let's import testing. Testing, and we can say, okay, let's say we have int1 is an integer with value 3, float, or int2 is an integer with value 5. And then we say, you know, result is add int1, int2, and then we would expect, no, not slice. We would expect this to become 8. Okay. Now let's try and run this as a test. Oh, we need to add that try here. And it passed. So you can see if we change this to, let's say, a 7, it's gonna be an error because it expected 7 and found 8. Alright. But that works. And then, but let's change. Well, let's add another one that should fail then. So let's say we have a float now instead. And we try to add the float here. We should expect this to fail. I'm just gonna set this to 8.5. It doesn't matter, but when we run the test now, we should get a compiler error because you can't add an int and a float. Cannot add a generics int with a generics float. Generics is just the name of the file, so that's why we get this. So there you have kind of like, you know, yeah, polymorphic types, or yeah, whatever. The anytype is kind of like, it is kind of polymorphic. It can turn, but the thing is that it can turn into anything. So you have to kind of set the limits yourself. And the downside is also that the constraints aren't really that visible. It just says anytype. So you're wondering, okay, what do I actually put here? You don't actually know unless you know. You know, unless you go in and read the code, basically. So that's a downside of this. But there is one more thing we can do. Let's remove this one. Okay. So this one is gonna be I'm gonna call it like interfaces with vtables. Oh yeah, hang on. There's also another thing you could do. Is that you notice here that we called, or that we accessed value. That just happens to work because both of them have value on it, and that's also pretty nice. Now, if they would have the same functions on it on themselves, basically, if you have any type, I mean, an easy example would be to kind of, you know, let's say we have a thing called stringify, and then value any type, and then this would return like a string or something, let's say. Now we could just say value.stringify, let's say. You know, you can pass in anything as long as it has a stringify function. This will be a compiler error if it doesn't have a stringify function. So this could also be considered to be kind of like a generic here. All right. Now the last one is vtables. So basically this is how the standard memory allocator works, which is kind of like an interface, you could say. It is a generic because you can pass an allocator around everywhere, but the implementation could be different. So what would we do then? Well, I guess we can continue with the number theme. So let's say we have I mean, okay, let's try and make an expression. This would be like vtable. The vtable version here. Okay, so this would have, first we would have like a pointer to, which is an any-opaque, and this is a pointer to basically the data that's needed for the implementation of this interface. And then you would have a vtable, which is like the collection of function pointers that implements this interface. Let's call this interface instead. I'm not gonna say I-expression because that just doesn't feel sig to me. Okay, so we have a vtable. Now this is like a struct that keeps all the different functions on it. So let's say we have a expression evaluate. Let's say we have a function called evaluate. Now this is a pointer to a function that will take, first it takes an any-opaque, which is the kind of the data that is needed to run the interface. And yeah, I guess that's all we need here for this case. But you can have other, you know, if you have other functions that does the same, like for example allocator has alloc, and that's a function that takes any-opaque, and then it also takes like well, I believe it takes also like you know, a type, and it takes you know, the length, like how many items do you want to allocate. But anyway, evaluate only takes one thing, which is the context, and then we get yeah, some kind of value out. So I'm just gonna use like let's import standard. I'm gonna use like standard JSON value because that's a very generic thing that can be basically anything. That is a JSON value. So let's say we do this. Okay, now we have our little interface here. So this would actually be the thing you will pass around. So then we have a function here called evaluate, and we need expression interface. Actually, I think this is actually a pointer, if I'm not mistaken. No, it doesn't matter. No. Okay, because the values inside are pointers anyway, so it doesn't matter. Okay, well, anyway, so evaluate, and then this returns a value. Now this would just call self-evaluate self-pointer. So we just call, well, no, self-vtable self-evaluate. So you can see here that, you can kind of see here that when you call evaluate on the thing, it depends on what's in the vtable, right? So if you set the vtable to be some other implementation, then it changes. So let's implement this now for a couple of things. So let's have like a number expression, and this one has a value which is an i32, let's say. Let's have a function called evaluate, which basically just takes the number expression and actually let's make this into the vtable. Actually, yeah, we will have the vtable here, and this will be okay. Let's extract this into a type, actually, vtable, so that we can use it. And this is just a vtable there. And then you will have number expression. Let's make like an init function, actually. Values i32, and then this would actually return an expression interface, right? Because this is the type that we're gonna pass around to all the functions and stuff. Okay, so this is the expression interface. Now, what's gonna happen is we're gonna create pointers. Usually, wait, how did this work? Usually pointers just set to undefined, and then the vtable is, well, that's for the allocator, I guess. The vtable evaluate is equal to, and this would be itself evaluate here. So we create a function here. We need to grab the pointer, which is aniopaque, and then we return a JSON value. So this needs to be the same. This function needs to be the same as the one we're trying to call here, or the one in the vtable here, yeah. So this would be, first we have an aniopaque, so we need to convert the aniopaque to our expression. So we have our thing here, and this would be a number pointer to a number expression, which will be pointer cast, and I do believe you need to do an align cast as well. Pointer. So now we convert this aniopaque pointer, which basically means it can point to anything, into this number expression. Okay, and then we just return, you know, the value, except we need to create like a JSON value. Well, we don't need to do this. We can do integer equals. All right, and this is an i64, but that should be fine. Okay, so that's our evaluate function on this specific implementation. And when we call init on here, we will this function you could put anywhere. It doesn't need to be on here. You can put a function here, but then it kind of defeats the purpose of this being like an interface. But you could put it outside to have like a number expression or something. But this works here. But the only thing is this part here, because the pointer, it needs to be a pointer, right? So if this is like undefined, how does this work? This is the part where my brain is currently stuck at here. So how will this work? I mean, what you can do is you can go to the standard memory allocator and check. Because here it got the same thing. We got the pointer and the vtable, which apparently is a pointer to a const vtable. And then you have all these functions here that take any opaque and so on. And then when we, where is, so let's go to standard heap, and then let's go to like general purpose or something. Okay, yeah, so usually how it works is that you would create, let's actually go to main. This is how it works, usually here. You create a GPA, which is not an allocator, it's a general purpose allocator. But then you call allocator on that to get an allocator. And now we actually have a pointer that we can use. Right? And then this sets all the vtable stuff. And we get an allocator that has a specific interface. Okay, let's continue here. So, okay, so init doesn't really work. I'm gonna say, well, actually, we cannot actually do a thing there. We just do this, and we return value equals value. Okay, this is just for convenience here. Then we do a function called expression or something like this. Self is number expression, and we return an expression interface. Now we will do pointer equals to self and vtable wait, how did I do it? The vtable, where is that? Vtable is just this. Okay, that's interesting. I guess because it's constant, maybe it works. I don't know. Sure, let's do the same thing so we nothing gets messed up here. Okay, and this has evaluate equals evaluate. Okay, so how we can use this now is that let's do a test, and we'll do testing. So let's say we grab a number. No, actually, also what you can do now is you can do evaluate expression. So kind of a basic example here, but this is how you would use it now. So you could do like expression is an expression interface, because you can pass this in, and it could be any kind of expression now, but it is typed to be an expression interface. So it has to be an expression interface. So that is good because it constrains it to that. And then we get the JSON value out. And this, of course, is very trivial because we just call evaluate on it. But now this could be any kind of function. So you could also have something like a state machine, or not a state machine, but you can have a state scope that can potentially, if you have an like if you extend this system, you can add that the evaluate function actually needs a state or a scope that you can then change. And the point that I'm trying to make is that you can implement another interface or another one of these that will kind of register stuff on the scope, for example, or an identifier that will grab the thing from the scope, you know. So you could do the whole script like the AST evaluator like this instead if you want. Because yeah, you could call evaluate on the expressions themselves like that. And then you can turn a number into an expression interface, like generalize it basically, which is kind of interesting. And then okay, so then we just call evaluate on it. We don't know what underlying type it is, because the interface, this is just an opaque and this is a vtable. So I mean, technically maybe you could introspect the vtable, maybe, I'm not sure, but actually maybe you can't. No, you can't. This is a runtime value, and this is, both of them are like runtime values. Anyway, yeah, so that works. So you would be able to get an interface and call evaluate on it, and it would depend on which type it is. So then we have a number is gonna be a number expression, but you still have to like create the number like this, let's say, and then if you want to call like result is gonna be evaluate expression, you know, if you want to have the expression, you actually have to wrap it like this in the expression interface, so to speak. So it's kind of like just wrapping it, to be honest, but it is a way to speak about this a little bit more generically. And then we do like expect equal 3 results. Yeah, I guess integer. And then we run the test, and we get some issue 103. Oh, it's because this needs to be a var, I think. Yeah. There we go. So there we go. There's 3 different ways to have like kind of generics in Zig. The thing that I found fascinating is basically the comp time stuff. Like you can have arbitrary rules in the comp time stuff that you can sort of define yourself. Like here, like you have like, okay, well, you can do left and right has to be ints or floats, but they can't mix and match. So kind of like you can do any, and then you can do introspect on the types. You can do like type info, switch on this to check if it's a you know, pointer. If it's a pointer, you can like unwrap the pointer to its child, you know, child type and stuff. So you can do all sorts of stuff with that, which is kind of cool. And that's like where I like to explore a little bit. I think the new IO writers own the interface. Oh, I see. No, well, I'm not sure actually. Oh, they own this though. Well, they have this stuff. I guess they have like the super generic things that always gonna be required, maybe. vtable. The thing that's missing here is generic writers. Like writers to with other types than bytes. But then if you go to like file and you go to writer here, where is the file writer? Yeah. You have to if you want a file writer, you have to create this first and then call I'm pretty sure, and then you call just then you can access interface on it. But what is happening here? Init interface. This doesn't need a writer. This just inserts the interface directly. With a buffer. how this works, because where would it know? How would it know which file to write to? I mean, it's in the standard library, so it should work, right? But yeah, I don't know how this works. Oh, wait. Send file writer. Drain data. Okay. Anyway. Okay, well, anyway, this is how like the allocators work anyway. So yeah, to recap, we have the union enum, which is arguably like the easiest way to do it, where you just have a union enum. Each type can have its own implementation as well. So let's say, you know, instead of being I32, let's say you have like you can have a struct that is like evaluate. You can have a function called evaluate here as well. So okay, let me show you this last thing about union enums actually, and then this would be, well, if they're gonna have the same type, well, it could actually be this. Let me cook here. So this would be self this values I32 return self value. Okay, and then we have the same thing here. We have a struct. Normally we probably put these in separate types, but I'll just put it here for demonstrational purposes. And this returns a value. Okay. Now the union enum itself can also have functions. So now we can put an evaluate function on the union enum itself, and this is an expression, and then we can, yeah, let's just do like a JSON value for easiness, and then we can do a switch on self, and here you can do inline else, which kind of expands all the branches here. It expands, like we have int and float, so you will get two branches, ints or floats, depending on the runtime value of self. And then you can get the value out here, and you can call evaluate directly. However, they do return different values, so we have to actually do this now. But I mean, if you want, you can also do like int, and then you would know that it's an int, and then you can like wrap it into, you know, a JSON value integer, for example, with the int dot evaluate basically. So you can do that as well, but if you just call inline else evaluate, you have to have the same you know, type everywhere. But this also works as kind of like an interface where expressions are the thing you pass around. You can call evaluate on it. Evaluate will actually then go ahead and check which tag we have, and then call the appropriate function from that. So this is also a very nice and easy way to implement kind of like interfaces. Like if you know up front which types you want to use, then it's very good. This way is very good. But if you don't have everything from the start, like if you want to create some generic interface that is going to be used maybe people want to create their own interface, like implementations here, but still be able to pass it around to be used by others, you know, then this is a very nice way to do it, because you can pass around this value around, this type around, and they will be able to use your implementation without any issues. Which is the case of allocators, for example. All right, that was a little, you know, rundown of the generics there. Because someone asked, Rocket Sammy, you. Hope you enjoyed that. Okay. Back to this stuff. Where were we on this? Thank you, Isn't. Does this work now? Yes, it does. Okay, so it works. Yes, okay, yes. We were doing the evaluator, that's right. Evaluator. Right, so we're kind of in the same pickle here. Let's do maybe... should we just do this easy way first, maybe? If left is an integer, so this is kind of the same thing here, and right is an integer, we will return an integer which is left.integer plus right.integer. And since we want to have protection here, I'm just gonna say it maxes out and not wraps around, because that could be all sorts of weird issues. Let's just max it out. It's not gonna max out, it's an I64. It's not gonna max out. Normally. Okay, like if you're iterating or something, I don't know. Return. Alright, so that is one case. If we fall out, we are going to return an error, binary expression not supported. Or okay, I guess we'll do unsupported binary expression. Okay, so now we should be able to add integers together. Everything else is not supported. So if we try to run this now, we're gonna get unsupported expression. Wait, why do we get unsupported expression? Also, I need to disable the logs here. Which means that this is not used anymore, so I can remove this. Hey, Polaris, thank you. And back to you. Oh, it wasn't working? Okay. Switch was handled all possibilities. Right. So I'll just fall through here. Unreachable code. Oh, I see. We do a return there. Okay, well, let's do no, we skip the return. And there we go. There we go. Now it should be built. Unsupported binary expression, because we have also a multiply. And I mean, sure, I'll just copy this for now. We have to find some kind of better way to do all this. I'm gonna do multiply. Does this even exist? I guess so. I never used multiply, whatever this is called here. Yo, Penguin, welcome back. Okay, so apparently it works now. Let's echo this. What would this be? 6, 12. Unexpected token while parsing, no breadcrumbs. What? Okay, we get a parser issue. Perhaps it has to do with our arithmetic stuff. Operator equal bang equal, else if it's a terminator we will break. Is this consumed or what? No. Should we consume it if it's a terminator? It depends on what we're doing here. This is looking for what? End. What the hell is that? Oh. End of files. Oh, parse until end of files, right. Parse and skip lines. Okay, I guess we should. If it's a terminator, we probably don't need to consume it though. Okay, what's going on? So expression terminator. This should like include new lines. Yes. Because we should be in operator mode, and then we get a new line, and then we break. And then Aditya, will AI replace devs? Only time will tell. Personally, I don't think it will replace all devs, because even if AI is like, I don't know, perfect, well, until it's like absolutely perfect and can solve every problem, we still need developers to look into it. Maybe, you know, but and the problem there is basically it's going to be a competence issue, because you're gonna have, in order to find people who are competent, they would have to work as developers. So you can't just replace, basically, like right now, you can't just replace our juniors with developers, because then you will run out of developers. I mean, that's how it works in like all lines of work, I guess. Like, if you want to have people who are competent, you have to hire juniors as well to kind of keep the, you know, pool of people that are competent up. I don't know. It feels like I don't think they will get like perfect AIs. Although I did think that AI wouldn't be able to code like before. I thought that was like gonna be super hard or super impossible. Like when the AI first started the code, it was super terrible at coding. Like when ChatGPT first came out, I think coding was one of the still hard problems. I believe, if I'm not mistaken. But it was, yeah. But then somehow it got better and better. So I don't know. Yeah. It could happen, I guess. Okay. Okay, it might have to do with parse, maybe. Maybe. Because we can have like an identify expression, and then we do parse maybe here, right? So this would be a string as the second one. So first we have like an expression which is an identifier, so that's fine. Then we have then we don't have an operator. We actually have like a string, which should be an unexpected token. Okay, so that's why we get unexpected token. I see. Okay, instead of unexpected token, actually let's just return a null here. I think we should have an unexpected token. No, let's not have it. Let's just have a null there. Expected identifier got string start. Oh, but did we consume it? Oh, we need to restore. Still fails. I need to build. Yeah. It's a hard problem. But I guess it's kind of like some technologies and knowledge has been lost over the years to do like, I guess, outdated stuff. Like if we could have an AI that could do everything, just rely on that, then that's fine, I guess, until the AI breaks down, maybe, you know. But the same is kind of true now. Like if you put like a bunch of people, if you take a bunch of people from the city or something, just as an example, and put them out in the forest, and they have to like survive on their own, they won't be able to. Well, there's a lot of knowledge that's lost that we don't really need anymore, and that could be the same for programming, you know. Unfortunately, but yeah, let's hope. I don't know, man. I think it's just fun to program. Also, like programming is fun, so you could still do it as a hobby. And also, you would need people that actually like maintain the AIs or evolve it. So I think you're always gonna have some kind of demand for it. I guess time will tell. It's a lot of changes happening. But if you say like right now, it's more like learning to use AI as a tool to help you be more productive. So that's what I'm doing. Like I'm and also people at where I work right now, we're trying to learn how to use AI because it has gotten so good that you could pass off some tasks to AI while you're doing something else, and it would just increase productivity. So that's really cool. Or investigate a bug, or explain how this works, or there's a whole bunch of use cases in the workplace where you could use AI very efficiently. We just need to learn what it's good at, so that we can use it effectively and to increase productivity, basically. All right, so let's see. I'm just gonna see if I can fix this, and then I have to go here. Why do we get this? We're at parse script, parse statements until blah blah blah, statement expression, identify expression, parse pipeline. Oh, it's a pipeline stage that gets messed up now for some reason. Interesting. So let's go to that. Parse pipeline stage. Okay, and it expects an identifier, got string start. So probably this is where it happens then. Right, so I think it's because we consume it at some point. So basically here, parse identifier expression. This is called from parse expression, I believe. Yeah. Where we try this first, but before that we actually did this. So it would have to depend on if we actually consume the next one or not. We restore the snapshot if this fails. Snapshot is taken here. So I think we're fine there. So if we go to, then we have identifier expression as well. Here we peek to get it. And we also try to do this. Which should restore itself once it understands that it's not this. Yeah, here we're picking, we're getting an identifier. At the end, we then do next token, right? And then we should be in the operator mode and look for this, but we don't find it. And we don't get an terminator. And we restore the snapshot. It could be that the restoring snapshot part does not actually work. That could be what's happening. Let's see if I can run test on this file here. Yeah. Let's try making a test for restoring. I'll just copy one of these. This is like the AI doing stuff here. Lexer restores successfully. I don't know. Okay, so we will have an expression that is like echo. Actually, let me test one thing first. If we do this, will that parse? No, not parse. Print. It does not. So, very good. I'm just gonna try to see if the restore works. So let's just do echo a same thing. Expected tags is gonna be identifier. Well, I don't care about expected tags actually. Wait, this is the wrong play. No, no, yeah. I'm trying to see if restore works. That's fine. Yeah, okay, fine. This one, and then we have a string start, and then we have a string text, which is empty, and then we have string interp start, and then we have an identifier, and then we have string interp end, and then I don't remember if this counts at the end here, but let's do this for now. Expected tags, next tokens expect equal. Sure. Let's also make a snapshot then. Now this it's the stream we want. We want the stream. Yeah. Okay. And then here's the snapshot. We do this. We expect them to be the same. And then we will restore. And now we should be able to run this again. Okay. I was expecting it to fail, but okay. It apparently works. What if we already have tokens in there though? What if we have something before we get there? So we have like comment. Now we should have, I think we skip the comments in tokenizing actually. So we have like 2 new lines. Huh. Actually, you know what? No. Yeah. What we do is we will do like, I don't know, 2 tokens, and then we take a snapshot, and then we do the rest, except now this is like 2. We take away 2, and we restore. There we go. Now we get an issue. Well, it might be something else. Non-matching for loop lengths. Oh. Okay, let's do this 0 to 2. Yeah, okay, it still works. What? Okay, well, I guess that's good. Then there's something else going on. Maybe. Let's try double. Let's try taking a snapshot here. Let's try take like first snapshot or original snapshot or something. Snapshot. And then this is not a try right now. No, that would have worked. And then we do restore on original snapshot. And then we take this one, try again, except now we do on everyone. You need to be a bar. Okay, it still works. Okay, so the restoration seems to work. I don't know why I'm banging on this here. Let's but then what is happening? Let us go to run script, parse stuff. Let's enable, oops. Let's enable logging. I should really wire that up with a tracer system, because the AI actually made like a more sophisticated like tracing system, which is meant to be like the logger that you could like pass in. You can pass in an environment variable from outside, and it will determine what you want to do. Okay, but now we have these things. Script parse statement. Now we can see the whole reasoning here. Maybe binding, maybe function, maybe okay, expression, identifier, pipeline, pipeline stage. Okay, so for some reason the identifier expression, like, it shouldn't consume this. I'm pretty sure. I'm gonna try this. What if we just disable maybe arithmetics? Do we still get an issue? Oh, now we get a panic. I see. I don't think this was here before. Or maybe that was like in release mode or something. Alright, 135. This is apparently larger than end index 0. Where does this come from? End column. Right. That's weird because the lines are has to be the same, otherwise we return. Still get. I was thinking maybe it's because it's like EUF there. No. Why is this happening? Okay, I guess we'll check if the span end is less than or equal to span start. We return as well. What? This ends the token, and now we go through here. Line 6, column 6. That's this, that's that. And then the end to start. What? No, P start. Okay, the peaked, right. Okay, so if the offset is different, but the line is this way, it's the same, yeah. Of the peak. Now why would the end be 0 though? Yeah, why would this be 0? Of the peaked one, the line is the same, it should be the next one. Maybe it's because it's the like EOF or whatever. I'm gonna say that this has to be larger than this, so I'll just do like larger instead of. Okay. But now we lost. No, we didn't lose. Okay, did we solve the issue? There's something weird going on here. So that works. Line 6, column 6, forest pipeline. Yeah. Then there's some stuff here. Yeah. Alright, so that's all the parser there. And then we get this out here. We get Command A. Okay, cool. So what's the issue? I don't remember what. Okay, whatever. Let's do this now. Okay, we got the AST. Let's do execute. There we go. Finally! Ah! Alright. Let's do one more thing. Let's do, I want this more than 11. I want this expression to work. And then also 11 plus, I don't know, 2. So this would, let's do like, so 10, actually let's do like 1, 10, this should be false then. Because this is 12 and this is, so this should be like the lowest here. Which means this is gonna get grouped and this is gonna get grouped. Also, I don't need parentheses. I wanna try parentheses as well, because that should be like built in to the expression parser. Alright, now this won't work. This will work AST wise, but not script wise, because we have unsupported binary expression, because we don't have expression for this. So, and then we should also be able to try like and false as well at the end. But let's do this one first. Maybe we'll get to and as well. Let's do this one. And then it's gonna be, then that's gonna be it. Because this should be pretty simple now. If we go to evaluator. And we add another one for greater than. And if both of them are integers, we do greater than. But now this is a bool. En or bool. Which one is it? Boolean? There we go. All right, and that's it for the binary expression. And we get 1, which is the string coercion of a bool, which is true. Okay, so let's try if we increase this to 6. Now that should be 0 false there. Hey! Awesome. Well, that went so fast. I think we want to do this as well. And false, let's say. This should be an unsupported binary expression or not. Attempted to use null value. Parser to A1. Okay, let's go back here and we will do this again. What? How does it fail here now, like all of a sudden? That doesn't make sense to me. It should fail. Okay, that doesn't make sense. Okay. Oh, I see. We're not logging. Okay, we're not logging the maybe thing. Yeah. Breadcrumb. Parse maybe arithmetic. And yeah, this is kind of like we're not really like we don't have breadcrumbs here. We're just looping through each and every one here, but maybe we could add breadcrumbs here in order for it to kind of show what it is doing here. So we could do like breadcrumb inner, or yeah, no. So because that will like, and I will do like parse arithmetic expression identifier. And this one should handle itself because there's a parse expression here. This one is a literal. You are an operator, binary operator. And then that one is done. All right, and here we have parse arithmetic. Which does a whole bunch of stuff. Let's not worry about that for now. So now we get a little bit more information here. All right, now we're seeing it actually parsing out this. So maybe, yeah, it's starting here because it already did this one, I guess, maybe. Which is kind of weird. binary operator, literal, binary operator, literal. Not sure what's going on here. All right, literal, and then we get a null value. I guess we don't have and here. I guess we don't have support for and. But we do have and or. Do you not have and? No? Where's the keywords? Lex identifier. Wait, how does this work with keywords? I do not understand. Okay. Next. Go to next. Next. Next inner. If we are in a string, we do this. If we start an interpolation, we do that. Skip white space and comments. If we're at the end, we do this. We peek the character. If it's this, which is not. And then we go here, is identifier start, is alphabetic. Then we do identifier. We advance until we get this, and we just do, oh, identifier tag. Here we go. Here we go. Keyword map. Aha. We need to add these here. Or there we go. Yes, okay, now we get unsupported binary expression. Great. Let's go back here, remove this. There we go. Okay, so back to the evaluator. Actually, let's do this first so we can see that the first one should be the and, yes. The left one is this whole thing, and then the right one is the false. So that works. Okay. And then we should have an and. Or logical and. Now the left and right needs to be booleans. And there we go. And let's just, I mean, or is gonna be very simple as well. There we go. And there we go. Now that works as well. And if we add like or true, we should get 1. Hey! It works! Ugh. Okay, let's try parentheses. No. God damn it. Why is this not working now? Unexpected token. Expected identifier, null, true, false. Got and. Okay, this pointer is kind of wrong. Parse primary expression. Wait, but that should end here. Or are we consuming the terminator? Oh, we shouldn't consume the terminator then. No, we don't. We just break and that's it. Okay. 1 second. It might be that. Well, okay, so parse expression. The primary is at the. That's the last thing. So we're doing this first. Here. And now if the. Maybe we should just do like left parentheses here instead. Oops. Oh, it's the wrong one. So this one. Yeah. So we'll do the left parentheses here. Instead, of in primary expression, or I mean we could have it there as well, I guess. Segful. Okay. Peak parse. No, we should do self next first. There we go. What, we still get the issue? Okay, let's see what's happening. So we parse this expression, right? But this is going to be part of the thing, yeah. So actually we should parse a maybe first. And if this is a, this could be a left parent. Okay, yeah, it's a left parent. We consume it. We parse an expression. We expect a right. And then we're done, and we should now advance to an operator. Actually, when we parse the expression, okay, we parse the expression. This should now basically go in here again and do all this crap again until we reach the terminator, and then we break, but the terminator is never consumed. We break and then we do this, which will not advance any further. Man, my brain is starting to get fried. Yeah, I should really quit here soon. I should have quit before, but yeah, what can you do when you have stuff to do? All right. Hang on. Yeah, it goes in here, it parses an arithmetic expression, we get it out, we expect the right parentheses, we do continue, so now we should advance the state, and peek the next token, which should be an AND at this point, which is an operator, which makes sense, because that's what we need. So it's an operator, we should match this, it should do this, and all that. And then continue, consume the token. So where is it going wrong? Yeah, we get here to the end. Now we're doing a bunch of arithmetic expressions, and then we parse a statement. What? Also, why do we get to primary expression? We should get to the arithmetic here, not primary. Okay, that's wrong. We shouldn't go to primary here. Oh, I see. We're peeking like the two next ones. If it's a binary. Okay. Okay. Maybe we should just parse arithmetic actually. Maybe just we don't care about doing that. We just try to parse an arithmetic. If that fails, if it succeeds, we return it. Otherwise, we try primary expression. Ugh. Hey, it runs, and it works. Awesome. Okay, now we can do basic arithmetic. You can do Boolean algebra, sorry, and then and yeah, you can do this, but you can't use any other operator. I guess I'll just add the other ones because they're so easy to do. Just so I push something up that is, yeah. This only works on integers right now. It's gonna be a whole bunch of copy code. I wanna find some kind of pattern here instead. But I mean, I guess what you could do, binary evaluator. Let's have like add. We'll have the different operators, I think. And then we have like left anytype, right anytype. These will work directly on the actual zig data types. And the result will be binary result of type of, no, actually, this will be like add, or let's do like numeric. Oh, not any type. This is right and left. Let's just take the one because no. Let's take both because yeah. And then we have like numeric is a function that takes left and right, and then you return a type. And then basically like if left is it's gonna have to be the same, you know. If we go to, is it AST or interpreter value? I forgot. Is interpreter value. What I want to do is I want to add the integer type is an I64. Yeah, I guess the string type is that. The float type is F64, and so on. So let's do that. And then this is an integer, this is a float. Just so we can do like use the same names and stuff. So if this is a valued integer and right is a value integer, then we will return a value integer. If left is a value integer and right is a float, we will return we will coerce it into a float, which could be out of bounds because the I64 it could be, but whatever. And then we do like left is a float, right is an integer, then this will also be a float. Or if left is a float and right is a float, then it's a float. Okay, that's the numeric. Now we could also do for strings, like if a string plus string becomes another string, or if a number plus string becomes a string, you know. But let's just do numbers for now. So we're coercing like integers into floats if you add a float with an integer. We could just do away with the whole type, integer type, and just use floats. That's probably way easier. But whatever. Let's just do this for now. And now this is simply left plus right. Or we can even do this. And here we'll do subtract. And it's the same thing. Multiply. And divide. Now divide is a little bit different. Maybe. I think divide should coerce them into floats actually. Division. Yeah. We just return a value float here. We don't care about these, actually. Unless they are... If left is a float or left is a integer and right is a float or right is an integer, then we return that. Otherwise we're gonna have a compile error. Numeric expression by numeric binary expression not supported for type name left and type name right. Division expression not supported for. Okay. So we have the basic arithmetic stuff. Let's add logical and Boolean algebra. Logical or okay. Now they both have to be booleans, so well, it's just gonna be a bool, and right equals to bool. So actually, if they are both bools, then this could just be a bool. We don't really need to have any type here, and then you are really not needed. Actually, this whole thing is not needed at all. Yeah, okay. Okay. we also have like greater than or greater, I guess. And this would be like comparison, I guess. I mean, it's always gonna be a bool. And then we don't even need this. So, because the compiler will do it for us. Okay. I guess the idea is to make this a lot more simpler. Let's say we have like left and right, like we have the binary expression. Actually, we might need no. Actually, this has to be like expressions, I think, or maybe not. Because what I was thinking is basically something along the lines of like return left value, or like, you know, apply operator, something like to the likes of this. And let's just have like left and right, and then the operator, which is like a binary operator, right? And then you would kind of map the operator to one of the functions. But I mean, it just ends up being more work than just copying these around, I guess. Yeah, whatever. Let's just copy it manually. God damn it. Okay, well, let's do these. So we have like floats, 2 floats. Make a float. I guess you could do for numeric stuff. You could probably do stuff. But and we can also do like, no, we can't. left is integer and right is a float, then we do integer and we cast it float from int. Now there could be an overflow there, but or an error, like casting error. Float right is integer, then you would be float from int. See, this pattern is basically going to be copied against all the numeric operations. So that was what I was thinking, like maybe we could capture this pattern generically, but so we have like integer produces an integer, float and floats produce a float, integer float produce a float, and then we also have to cast it. Float and integer produce a float as well. We have to cast it as well. Wait, this is float and this is it. The only thing that changes is the operation. And the result. And how we access these things. But it's the same. Well, no. The only thing that changes between these different operators is the operator itself. Which could be captured in a function that receives any type. Yeah, so basically add numeric, add left anytype, right anytype, and then this is basically gonna be numeric. Okay, it's the same thing that we already had. You know what? Maybe we could do this. We could do const x equals is left equals 0, const y is right equals 0, return type of x plus, no, that doesn't work because that doesn't do the same thing that I want to do. Okay, so if left is value integer and right equals value integer, return integer. If both of them are a float, return a float. If this is an integer and this is a float, return a float. If this is a float and this is an integer, return a float. It's kind of like an, is this an XOR? No, it's not an XOR, it's an OR. If integers are 0 and floats are 1, it's an OR table. Unsupported numeric binary expression between left and right. Okay, so we return left plus right. However, no, we can't just do that. We have to basically copy this and we have to say also, wait, no, we'll return a value. Actually, we'll return a value. Yeah, we just return a value. We don't even need this here. We just return a value. Yeah. There we go. So if left. Wait, and then we can just grab the values. No, what the hell am I doing? left plus right. But the types doesn't work. Now we'll cast it in before. Oh, this is breaking my brain. Yeah, I think it's kind of like what I'm trying to do is I'm trying to say, let's say we get the operator evaluator is, you know, let's say we have a map of, you know, or we're switching on binary operator, and then we'll get a bunch of operators. You know what, let's just copy the code. God damn it. All right. I give up. I have to quit anyway. God damn it. Divide. That is gonna be that. All right. Let's copy you, and we have subtract, and then you're gonna be plus 2 nines. There we go. That was way quicker, but extremely annoying. There's like several operations going on where there's a casting thing and then applying the operation. Actually, the operation always happens between the same types, to be honest. Like, it's either integer integer or float float or float float or float float. So but that would yeah, I guess you could have. Why am I doing this again? Numeric binary operation. Well, okay, let's do like com time t. This will return a type. This will return a function that will take 2 t's and return a t. Yeah, that's it. And then we have a bunch of those. So we're gonna have a function get binary operator, get numeric binary operator, which will return maybe a numeric binary operator of type t. Yeah. Okay, do we even need type? Yeah, we need type t because we need. No. We don't need this. If you are any type and you're any type, then you are type of left, because they both are always the same. Right. And here we're gonna get our comp time, or it doesn't need to be comp time, it can be binary operator, and we will get maybe a function that takes two any types and returns type of left. But that doesn't work. Okay. So I can't have this type. Yes, I can. Maybe. No. Ah. I guess you have to know the type before. Okay, this is gonna have to boil a bit, but yeah, okay. But now we have these. Divide greater also. Well, greater's actually a little bit easier because we basically just need to know if they're gonna be either. Let's actually do let's do an a thing here. Let's do like numeric value. Self is a value, and we get a maybe. Oh my god. Actually, let's just do a boolean. Is numeric bool return self equals integer or self equals float. But we can't return the actual number because it depends on the type, which is annoying. But we can do this now. So we can say is numeric and write is numeric. There we go. So that's a way easier way to check if it's just a numeric. If they both have to be numeric in order to do this operation, then we do the operation. However, now the value here is gonna depend, like we don't know if it's an integer or a float, and we can't have one function that returns, you know, the numeric value, because what will be the return type? It's gonna depend on the type, on the tag of the value, and that doesn't work? Question mark? No, because then this has to be like comp time known. Yeah, we can't do this because this is comp time known. No, that doesn't work, I don't think. Because, yeah. So we get like the value, the tag, and then we check like, now this tag is comp time known, but I think you can't have this value in here. And that was basically like if t is integer, then break, you know, integer else float, let's say. And then we call like numeric value. Now this would be an what? No, this oh my god. It does have a known result type. Okay. This value floats. Oh my god, it's even more annoying. Okay. Float left equals value float from int left float left, yeah, something like that. And I have to do it float right. What the hell? Stop! Stop! Okay, I think that's weird. I made a macro, and in the macro I called the same macro accidentally because I thought I had like exited the macro mode. And then it seemed to be maybe infinite loop, I'm not sure. Does this work, by the way? Like if we do, so let's do macro float from int. We do this const float left and then that. Does that work? Yes, it does. Okay. So like macro float from int, const float left, autocomplete, float left, const float right. Okay. All right. Are you satisfied? No? Oh. Okay. Fair enough. The wrapping or the maxing out doesn't work. Apparently. Is that like... But what if it maxes out? Okay, well, this part. Oh, shit. Okay, there we go. Okay, apparently you can't do that. With integers, or I mean floats. I didn't know that. And here, since it's integers, you have to use like any of these. So I guess we'll just... Actually, no, this is different. I want to turn them... Actually, yeah, I want to turn them both into floats. So we'll do like float. And then we do float left, float right. Just because convenience. We should really just do away with integers, to be honest, maybe. Right. So now we get here. This doesn't work, right? Okay. And now we don't have it. So I guess there's like no way around this, is there? Well, maybe we can do this actually. Is numeric or no, and right is numeric. Once we know that, we can just do left value is left is equal to integer, then it has to be an integer, so then if this is true, we will do a left of integer, otherwise it has to be left of float. So that's at least a little bit more terse here. Oops, there we go. And then we do like left value more than right value. Okay, so there we go. That's... But wait, what if one is integer? Yeah, this doesn't work. God damn it. For the same kind of reason, you can't do this. I mean, let's just convert this to a float. Oh my god. There we go. Okay, that's at least a little bit more reasonable. So now we can do all the different, like, greater, equal, oops, less, equal, what else? We have like equal, or yeah, equal and not equal, I guess. And not equal. There's the thing about comparing floats, but it should be fine. All right. What else do we have actually? Do we have anything else? No? Is that it? Remainder, that's right. Remainder, that's... Let's just do like divide remainder. I think we do kind of the same thing here. We just do that. No, wait. That doesn't work. Wait, is this a thing? I thought you had to do like mod. Unsigned integer, same as that. There's like mod F. Why do I get, okay, documentation there, I was gonna say. Returns the integer and fractional floating point numbers that sum up to x. The sign what? The sign of each result is the same as sign of x. Could you show me the result of the code? Yeah, 1 second. What the hell is this function? It's not mod, that's for sure. Okay, let's just do add mod because that should work. I'll just do this one and I can show you because that's the last thing I'm gonna do, and I'm gonna test it a little bit and that's it. So that we have like arithmetics and we have, wait, it's not, yeah, it is mod. All right, okay, whatever. Now we have all those. So here's the language right now. We can do these expressions here. Now what if we do, so now this results in 0 because we have 6, 12 is more than 13. Well, that's false and false. But if we add like or true, that should result in true. What else did we do? Well, we now support that, so I'll just add like and true there. That should be true now, yeah. And if we do this, that should be false. Accidentally pressed the thing there. We have like equals. So let's do like 5 equals 5, 5 equals 4. That doesn't work, okay. This shouldn't happen. Oh no, we already got that. Binary operation from token next. Yeah, you can see it is in its like super infant, not even, you know, thought of yet stage almost. Okay, we're trying to do from token with the thing and we don't have it. What is the token? Is it equals equals? No, we have equals equals. No, we don't have equals equals. No, that's just equal. Oh, a sign is equal. That's not true. That's just a sign. And that's not even part of this. There we go. Okay, there we go. Yeah, so yeah, 5 is 5. 5 is not 4. So that's 5 is not 4. 5 is not 5. Yeah, true. Yeah, first you get false, then you get true, false, true, false. Okay, I know this is riveting here. I just implemented this, I'm just trying it out here. You know, then you have like 5 is less than 5, 5 is less than or equal to 5, 5 is less than 4, 5 is less than or equal to 4. That should be all be true, false, false, true, false, false, true, false, true. I guess, okay, yeah, I guess we could do this. Now we can more easily see it. True and true. Highlighting doesn't really work for interpolations here. True and false. False and true. False and false. Checking our tables here. True and true 1, 0, 0, 0. Very good. True 1, 1, 1. It works. Yeah, and then potentially you could also get, well, you can't, you actually can't get like exit codes yet. You can't get exit codes. Or you can't compare strings, you can only compare numbers. I haven't tried floats actually. What if I added 0.5? Will that mess everything up? No, it won't. Cool. It would just turn this whole expression into a float. All right. Yeah, I mean, that's basically where we are right now. You can make functions as well. So actually, I wonder if you could do this, like test runic. Sorry about the snake case. I'm getting damaged by this convention. But we can't pass in parameters. I forgot about that. We don't have parameters yet. We do not have that. I mean, we can fake. We could do test runic sh, and this would be expression, and then runic. No, I don't have inline sources. I can't that could be something, maybe like executing just a inline script. That's actually, we don't do it. I mean, we could make a temporary file. You know what? We can actually do it from here, because we could run bash, but we can't receive arguments. That was the whole thing. Yeah, that's right. So we could do yeah, expressions 1, and then I'm just gonna echo this to see that it works. Yeah. Good. Okay, and then we will, I guess we'll echo. Now let's do print f. To temporary runic. And then we will run runic on that. Expression, yes. So actually this would be like echo how do you escape? I guess we could do like echo this. And then continue here. Echo x. No, yeah, because we need this. And this. And then we also need that. Oh, I see. Okay. No, I don't see actually. Whatever. There we go. I'm just practicing a little bit. But then we can do this all in one go, so that will be the actual expression, and that's the end of the thing. There we go. There we go. And now we can call bash test runic with 5 equals 5. Oh, because bash is a keyword, right? Well, it shouldn't be. Lexer bash. No, token. Yeah, I'll do like underscore bash. There we go. There we go. So now all to not repeat myself, basically. Bash test runic. Find this, destroy until this. No, this won't work. God damn it. It worked. Okay. Oh my god. Okay. I would have to implement function arguments to make this way easier to do, but yeah. Okay. Cool, but great. We've got arithmetic operations, we got Boolean algebra, we got all the things, comparisons, binary expressions are properly parsed with precedence and everything. You can have parentheses as well, and it all seems to work. And yeah, type coercion from floats to ints, or I mean the other way around. Actually, okay, one more test. One more test here. What is... I've always wondered what 1 over 0 is. What the... Oh, it's infinite, okay. I'm pretty sure that's wrong. Weird. I thought for sure we were gonna get an error here, but apparently it worked. I mean, I guess it's better than a crash, maybe. Okay, so what is 0 over 0? Negative nan. Sounds about right. So negative, not a number. Okay. And then let's add 2. Still negative now. Okay. Nice. Oh, man. We have arithmetic. We also have Boolean algebra. We have comparison for numeric. Yeah. Actually, does reassignment work for strings? No. String in arithmetic expression not allowed. What the hell? Okay, now I broke a string assignment. Whatever. Okay, that's gonna be it for today. Yeah. I'll probably continue on this tomorrow. And yeah, but that's gonna be it for this time. So thank you very much for joining me here, and we'll see what we come up with next time. So have a nice day and see you later. Bye bye.